Morning, everybody. Welcome back to Math 105. Plan for today is we're going to discuss the next two propositions in the elements, propositions 2 and 3 from the first book. And hopefully we will be able to finish off standard 14 today. As far as office hours go, I've got my usual hours today and Wednesday at 10 o'clock and at 2. And on Tuesday, I've got my usual hours at 10 o'clock in the morning, 1:30 in the afternoon. And as far as homework goes, keep in mind the standard 13 quiz is due tonight. And the standard 14 quiz depends on how today's class goes. If we finish off standard 14 today, then it'll be due Wednesday. If not, it'll be due on Friday. Any questions or comments before we get started today? All right, so a math major once faces the following question on a physics exam. You were given an accurate barometer. How do you use it to determine the height of a skyscraper? Student answered, go to the top floor, tie a long piece of string to the barometer, lower the barometer until it touches the ground, then measure the length of the string. Professor, who's a little unsatisfied with that answer, and asks the student and says, hey, that technically works, but that's not really what you were supposed to say. Can you give me another method that demonstrates your knowledge of physics a bit more? And says, okay, sure, go to the top floor, drop the barometer, measure how long it takes to hit the ground. Oh, that's not it. Try again. Okay, says the student. Make a pendulum of the barometer, measure its period at the bottom, then measure its period at the top. Try again, says the professor. Measure the length of the barometer, mount it vertically on the ground on a sunny day, and measure its shadow. Then measure the shadow of the skyscraper. This is ludicrous, says the professor. Again. Walk up the stairs and use the barometer as a ruler to measure the height of all the wells in the stairwells. Last chance. No. Find where the janitor lives, knock on his door, and say, please, if I give you the barometer, will you tell me the height of the skyscraper? Moral of the story is, there's often more than one way to solve the problem. Okay, so last time in class we proved Euclid's first proposition, the one that says, on a given finite straight line, to construct an equilateral triangle. Which in other words means that just using things that you're allowed to do from the postulates and the common notions, if I were to give you a straight line AB like this, we should be able to construct an equilateral triangle on it. Meaning make it a triangle whose sides are all the same length, for which your original segment AB is one of the sides of the triangle. And we did that with playing around with circles in order, and notice that Euclid had kind of this mistake where he had two circles that he assumed would have to intersect, but never actually proved. So what I want to do today is I'm going to go through the next couple propositions and see and start to get a sense of how do the propositions build off of each other. And in particular, today, I'm going to start with proposition 2. Where proposition 2 is going to say to place at a given point a straight line equal to a given straight line. Where again, though it doesn't explicitly say so in the elements, you can kind of assume that at the start there's like an inherent it is possible or it is allowed. And so what this means is that if we have a point A and a line that's going to go from a point B to a point C, what we would like to be able to do, or to show that we can construct, is going to be another line that's of the same length as the line from B to C, except this line is going to be include A as one of its endpoints. So in other words, we'd like to sort of be able to take the line from B to C and to shift it over, so to speak, so that that line can also start at A, but we would still get a line that's of the same length. Any questions about what exactly we're trying to prove? So, again, these proofs are entirely written out in the element, so if you just want to follow along in the elements, you don't need to necessarily try and write all of this down. But just like with our first proof, I'd like to kind of stop at various points and ask questions of how do we know we're able to do this sort of thing. So let's try and prove this. So first, we're going to let A be the given point. And BC the given straight line. Thus, it's required to place at A straight line equal to BC. In other words, what we already said. We have a point A off by itself and a line from B to C to start off with. And we want to be able to place at A some straight line where A is one of the endpoints. And we want to be able to make that straight line have the same length as the line from B to C. Again, only using kind of the same building blocks we had in our previous proof. The 5 postulates, the 5 common notions, and maybe some definitions along the way. So for the first thing we're going to do is we're going to say that from A to B, let the straight line AB be joined. So in other words, draw the straight line that goes from A to this point B over here. What's letting us draw that straight line? Which building block, in other words, tells us we know we're going to be able to join 2 points like this with a straight line? It's going to be postulate 1. I'm going to go ahead and cite that here. So, have a straight line from point A to the point B. I don't think we can immediately say, aha, let AB is the line we're looking for, because we don't necessarily know that this line from A to B is going to be the same length as the line from B to C. So we don't necessarily know that. We can't necessarily stop our proof right here and say, oh, we have a line from A. It's not necessarily the correct length. So that's not going to be the line we use. But now we're going to do something a little bit interesting. Going to say, and on it being the line AB, the equilateral triangle DAB be constructed. This line. So in other words, equals saying, all right, great. Take this line from A to B and make an equilateral triangle on this line. And we're going to call the third vertex we get from doing this D. So how do we know we can just do that? We're making an equilateral triangle on this line segment AB. We don't have any there's not a postulate that says, given any line, you can construct an equilateral triangle on it. It's not a common notion. So how do we know we're allowed to actually do that?
Our other proposition.
Yeah. So here, we're not going to cite one of our original building blocks. It's not just a single proposition, common notion, or definition that's going to allow us to do this. We're actually going to be able, the only reason we know we can do this is because of a proposition, something that we proved that we could use. And so our citation this time is not going to be postulate X, common notion Y, or definition Z. The way the book is writing it out is using this notation. I.1. Any ideas as to kind of what this notation means? Like, why is it saying like I.1 instead of proposition 1, so to speak?
Because I think it's book 1, proposition 1, because they're numbered. Each time you search a new book, the propositions are numbered starting at 1 again.
Bingo. Yeah. So here the I is just the Roman numeral for 1, basically saying that this is it's coming from proposition 1 in book 1. Of Euclid's Elements. And you're right, because every time remember, the Elements is not just a single book, it's actually made up of 13 separate books. And each time Euclid starts a new book in the Elements, all the propositions are renumbered again to start at 1. The common notions and postulates and definitions, not the definitions so much. The common notions and postulates, at least, are all the same from book to book. He doesn't assume new postulates in every book. He uses the same 5. But the propositions are renumbered in each book. So I think the choice of writing it out like this is to just make it clear which proposition 1 you're talking about, because there's a bunch of them. And oftentimes, this isn't going to be the case in book 1, but in a lot of the later books of Euclid's Elements, they're going to take as justification in some of their proofs propositions from previous books. So if we're trying to prove, so it might be the case that proposition 3 in book 5 actually requires proposition 2 in book 1 in order to be able to prove it. So that's why it has kind of this funky notation. Whenever you see this, just think book 1, postulate, or not postulate, proposition, whatever the second number is. This kind of makes things, it's kind of nice that we're able to use proposition 1, because we could have constructed an equilateral triangle using the same procedure we did on Friday. Take a circle around A of radius AB, take a circle around B of radius AB, find where the circles intersect, and construct an equilateral triangle that way. But the fact that we've proven proposition 1, or at least Euclid's satisfied that he's proven it and doesn't have any holes in his argument, is going to tell us that from here on out, Euclid doesn't need to go through the method he used to construct an equilateral triangle again. As long as he cites proposition 1, he could just then say, by the same procedure we did in proposition 1, I'm not going to go through the details again because I've already given them to you. But by the same procedure, we could construct an equilateral triangle like this. Any questions or comments so far? So we have an equilateral triangle. Let the straight lines AE and BF be produced in a straight line with DA and DB. So in other words, he's saying, take the line from D to A and the line from D to B and make it longer. So eventually we'll have a point down here, call this one E, and we'll take this line here, and make that F. So we're taking the lines from D to A and the lines from D to B and just extending them out and extending them onwards, just making those lines longer by producing them in a straight line with DA and DB, meaning just extend them in a continuous way. What's our justification for this step going to be? In other words, what building block is going to allow us to take our straight lines DA and DB and make them longer like this?
I don't know which one of them it is. I don't have my other notebook with me, but it's one of the problem. They're not the propositions, the original postulates. Yeah, few words.
I was going to say,
Yeah.
as you can see, that's tripped me up more than once.
It's postulate one,
Postulate 1?
I think, yeah, to draw a straight line from any point to any point, and we can use that, or, oh no, it's
There's another
postulate
one
two.
that,
It's, degrees of finite straight line continuously in a straight line.
Yeah, I think this one's going to be postulate 2. It's not going to be postulate 1 because we don't have points E and F to begin with. If we had points E and F that already existed out here, we could use postulate 1 to make a straight line from A to E and B to F. But we don't have these points already. We're using the postulate that says, given pre-existing straight lines, we can extend them outwards like this, which is going to be postulate 2. First time, by the way, that we actually needed postulate 2. Because postulate 2 was never used in proposition number 1. So now that we have postulate 2, we're going to start drawing some circles. And we're going to say, with center B, and distance BC, we're going to let the circle CGH be described. So with center C and distance BC, let the circle CGH be described. So in other words, we're going to draw a circle centered at B with a radius equal to the length of this segment from B to C. And Euclid doesn't explicitly say this in his proof, but in kind of the picture, but in kind of all the diagrams that you ever see going along with this proof, we're later going to know that he wants G to be the point where this circle intersects the segment from B to F. So he doesn't explicitly say this, but Euclid wants this point G to be both on this outer circle. I guess we also need a point H, which isn't going to matter. We want the point G to lie both on this circle centered at B of radius BC, but we also want this point G to lie on this line segment here, going from D all the way down to F, or from B to F as you prefer. And one thing I want you to note is that since this is a circle, we know that the distance from B to G should also be the same as the distance from B to what other point?
B to C.
Bingo. Since C and G are both points on the same circle centered at B, the straight line distance from B to C should be equal to the straight line distance from B all the way out to G. And in fact, that's good. And But before we explicitly say that, we're actually going to construct another circle, this time centered at D. And he's going to say, and again, with center D and distance DG, let the circle let the circles GKL be described. So now we're going to do the same procedure. We're going to make a circle, except this one's going to be really big because this circle is going to be centered at D and is going to have radius equal to the segment from D all the way out to G. So our circle is going to look something like this. It's going to go off the top of the board. This is a big circle. Circle is going to be centered at D and is going to pass through the point G. So all the points on this circle are the same distance away from D that G is. By the way, as a quick reminder, which postulate is telling us it's okay to go ahead and draw all these circles? It's going to be postulate number 3. Which is the one we used extensively in Proposition 1 that says you're allowed to draw circles centered at any point with radius whatever size or distance whatever size you would like it to be. So now we have a circle centered at B and a circle centered at D, both of which are going to be useful. So now we're going to start comparing some distances. Here's where the common notions are going to come into play. We're going to say that since B is the center of CGH, BC is equal to BG, which is what we already said, that since C and G are both going to be points on the circle centered at B, the distance from B to C should be equal to the distance from B to G. Or in other words, the line going from B to C should be equal to the line going from B to G. And that's just going to be from our definition of a circle, definition 15. So we know BC and BG have the same length. We can also compare two other lines. We can say that since D is the center of circle GKL, DL is going to be equal to DG. I forgot to label my points. L here, we're going to assume, again, Euclid doesn't explicitly say this and probably should. Euclid is assuming that L is going to be the point at which this big circle intersects the line from A to E. So here, Euclid's assuming that the length of this big segment all the way from D down to G is equal to the length of this big segment all the way from D down to L. I'm going to do like a sort of a triple hash mark here to indicate that. That the length of the segment from D to L is equal to the length of the segment from D to G. And now, here's the kicker. We know the length of the segment from D to L is equal to the length of the segment from D all the way down to G. We also know that the length of the segment from D to A is going to be equal to the length of the segment from D to B. We're going to be able to use our common notion about remainders, common notion 3, to be able to compare two other line segments then. If the length of the segment from D down to L equals the length of the segment from D down to G, we also know that the distance from D to A is equal to the distance from D to B. If we sort of were to take away these two line segments from the bigger ones, which other two line segments would we then be able to say must also be the same length? Using the fact that DL is equal to DG and DA is equal to DB, if we sort of take away DA and DB from DL and DG, which two line segments are we going to be left with that are going to have to be equal?
AL and BG.
Bingo. It's going to have to be the case that AL is going to be equal to BG. And if you notice, since BG is also going to be equal to BC, as we said before, that's going to tell us that AL is equal to BC, and AL will be the line segment we were looking for. The line that starts at A and has the same length as the line that goes from B to C. Because if you remember, that's what we were trying to find. A line that starts at the point A and also happens to be the same length as the line from B to C. Because those were our only starting pieces. So let's write that all down. You could. So again, since D is the center of B circle. So, and in these, dA is equal to dB. By the way, how did we know that dA and dB were the same length? If you recall, we knew explicitly dA and dB had to be the exact same length, but what about the way in which we constructed the point D told us that?
Well, it's on equilateral triangle, so all sides are the same length.
Bingo. It's because DAB made an equilateral triangle, we constructed it that way. So that tells us that all the sides, including DA and DB, have to have the same length. So in these, DA equals DB, thus the remainder AL equals the remainder DB. So AL is equal to BG, as we said, and this is coming from common notion number 3. Basically saying DL is equal to DG, DA is equal to DB, so if you were to take away DA from DL and DB with DG, what's left, the remainders, are also going to be equal. Because if you start with two equal things and you take away two equal things, according to common notion 3, what you're left with, i.e. these two segments, should also be equal to one another. So now it's simply a matter of getting back to saying AL is equal to BC and AL's the line that we're looking for. So now we are going to say, but BC was also proved equal to BG. Therefore, each of the straight lines AL and BC equal BG. And things which equal the same thing also equal one another. Things which equal the same thing also equal one another. Thus, AL is equal to BC by common notion 1. So AL is equal to BG by the argument we gave down there. BG was equal to BC by argument I erased over there, because they're lines that make up radii of the same circle centered at B. Therefore, AL and BC also have to be equal to each other. I personally think it's a little bit annoying that like every time Euclid uses common notion 1, he kind of feels the need to write it out as long and make it as long and tedious as he can. He doesn't just say, he never just says, AL is equal to BG, BC is equal to BG, therefore AL equals BC. He first always has to start by saying, thus each of AL and BC is equal to BG. Make that explicitly clear first. And then he always feels the need to kind of write out common notion number 1 in full, and things which equal the same thing also equal one another, thus AL equals BC. But agree to say AL equals BG, BC equals BG, therefore AL equals BC. Well, for whatever reason, Euclid really likes to make his common notion 1 arguments as drawn out as he can. And then we're basically done, because we can then just say, thus, at A, the straight line, AL is placed equal to BC. Being what it was required to do, or as we talked about last time, just simple QE. We have proved that which we wanted to prove by showing that if we just started out, because if you remember, all we were given to start with was this point A and this line going from B to C, we were able to show that we could find a line starting at A that happens to have the same length as the one from B to C. And through excruciating detail and multiple circles being drawn out, we were able to find the line. So what questions or comments do you all have about this one?
Did rulers not exist at this time?
Straight edges did. Rulers, I would say, did not. If you had a ruler, that would make this much, much easier. You could just say, all right, let's measure the length of this segment. Okay, I now know the length of this segment. I'm just going to start at A. I'm just going to pick any direction, go until I've reached the length of that segment. If rulers existed, a lot of this would become much, much easier. Including proposition 1 would still be tricky. But this one would become much quicker. As with the next proposition, as we're going to see.
If you use a compass and just set the distance from the one and then place it on A, make a little dash, put another mark on that dash, and draw a line connecting them.
Ooh, okay. So, let's erase this. So in other words, what you propose is we have this line from B to C, and we want to draw a line starting at A that has the same length. Why not just take your compass, set it to be equal to this distance, draw a circle around A with that distance, and then just pick a point like that, say, boom, done?
Yeah.
A good question. Why didn't Euclid do that? That would have been much easier than what we did. We spent like 2 boards worth of work drawing all sorts of equilateral triangles and circles and a gazillion other line segments along the way. This is actually a question I was going to have at the very end after we talked through Proposition 3, because something very similar happens there. Why do you think Euclid didn't just do that?
Perhaps he wanted to use his postulates and all of his common notions. He would have done all that work for nothing if he had just kept it simple.
Yeah, just like doing this. I mean, it's sort of doing this would only use postulate 3, basically, and postulate 1. It would use postulate 1, and that once you have your circle, you need to be able to draw a straight line from A to a point on the circle. But he wanted something that relied on common notions and such too.
Yeah, maybe he just really wanted to make it obvious that he'd done his work and he could reason his way to something through all of the previous work he'd done.
Could be. I don't know. He was just trying to make life more difficult for else. Just I want to use as much of my work as we can. We're lucky he didn't find a way to put the parallel postulate in here somewhere.
Is it because without a ruler you can't prove that D is equal to AC?
If we call this
You
point
can't
D.
just create a circle and say that it's automatically equal. You have to prove it. Without a ruler, you can't prove it any other way. Besides making all these circles.
I think that might be a little bit closer to the truth. That once you have this, like once you've done this construction, how do you then go back and say, oh, I know AD is equal to BC? Well, you can say I constructed. It's because I set my compass to this length, and then moved that over here, and I hope my compass length didn't change in the amount of time it took me to move it from this line to this line. And other than being able to say, after you constructed these, trust me guys, I know what I'm doing. I constructed it in this way. I would say, yeah, other than that, there is no justification as to why this line should then be equal to this line, other than taking Euclid's word for it that he set the compass the same way in both cases. Whereas over here, you get a much, much messier and annoying diagram, but if you're Euclid and you have all of this in front of you, you could then go back and say, oh, here's how I knew. It's because I knew from proposition 1, I could construct this equilateral triangle, and from postulate 2, I could make these whatever length I want. I'm going to make my circle here, centered at B, whose radius is BC. And in doing it in that way, I know that BC is equal to BG. Then I made this circle, and then doing it in that way, I know that DG has to be equal to DL, and since DL equals DG and DA equals DB, I could take it away, and so AL and BG, what are left by common notion 3, have to be equal to each other, when BG is equal to BC and AL is equal to BG, therefore AL is equal to BC. It's a lot more long-winded, but the visual construction, you could actually see a lot more strongly and smoothly from this. I think that would certainly be a way.
So with this version of here, making the different circles and just saying that they're equal, wouldn't that be more like Egyptian geometry, where they don't really need to prove anything, it's just sort of ballparking? Because they didn't prove anything, really. They just sort of did it.
The construction is a lot less kind of inherent. And it's really ultimately going to boil down to this. By the way, all this discussion we're doing is, you flip a couple pages forward, is basically what I was planning on discussing at the very last question in the packet. I think what it ultimately boils down to is, yes, there's something a little bit more imprecise about saying Euclid felt comfortable given a point A and a line AB drawing a circle, centered at A, of radius AB. He felt comfortable, given a point A to start out with, and a line for which A is one of the endpoints, drawing a circle. So basically just saying, all right, I'm going to draw this circle where I never have to drag my compass to be centered at one point to be centered at another point. I can just take my compass and construct it right here from the A that already existed. But he felt a lot more uncomfortable in a situation like this drawing a circle centered at A whose length is equal to a line that could be far away from A. But if A wasn't an endpoint of the line, let's say BC, he felt much more uncomfortable drawing a circle centered at A. Drawing a circle of that radius centered at A. Basically saying, if you want to draw a circle of radius AB starting at A, then yeah, then you just put the point that stands still at A, and you draw it out with your compass. And Euclid felt perfectly comfortable with that from postulate number 3. But if you have your point A over here, and if your point BC is over here, for some reason Euclid felt a lot less comfortable saying, all right, I'm going to set my compass up here, drag my compass over, and then draw a circle of that radius. So I would say you're right. If Euclid felt comfortable doing that, this would be a way simpler way to do it.
Isn't that just the difference between his geometry and ancient Egyptian geometry? He's actually trying to prove it.
I would say
that those lines are equal, unless if somebody didn't watch you drag your compass over.
that's true. You can't really prove this without explicitly having, I don't know, a video feed of you drawing the compass over and look, the compass size isn't changing as you do it. That would be a good way to describe it. It's a lot easier here to prove all your points on this circle are the same length because you just use the compass centered there, and it's kind of clear that like all of these points are the same distance away from A. Whereas here, once you come back later on and look at it, it's a lot less obvious that that's the case.
If he had because I guess what the difference is here is that he doesn't have a postulate saying, it is possible to duplicate the length of a line using a straight edge, or it is postulated that, So if there was a postulate that he's saying like you can duplicate the length of a line given another point, using a straight edge, setting it to the length. If that was a postulate, do you think? Because you could look at any of those circles and say that you don't know that they're without a video feed of it, you couldn't necessarily know that he didn't move the thing out. So I guess what the real difference is here is that he doesn't have a postulate for it.
You can move compasses around and draw straight lines based off that?
Yeah.
Yeah, he doesn't have a postulate saying he can do that. In fact, that exact statement is going to be what proposition number 3 says. So you can prove that you can do that from the postulates, but there's not a postulate in and of itself that says that, I would agree. I think there's kind of a lot of different reasons you can give for why Euclid felt a lot more comfortable drawing these sorts of circles than these sorts of circles. And I think all the ideas that you're all getting at are kind of good ones. And a big part of it boils down to the fact that rulers did not exist. There is not everything that Euclid did, he wanted to do with a straight edge and compass, and so he didn't want to have to worry about running into these sorts of issues. Any other questions or comments? Yes, that's a good question. Why didn't Euclid just do that? Because he felt squeamish about it, I would say is the very short answer. Because it's drawing circles in a way that's different from the way he wants to draw his circle. And I don't know, maybe he just wants to come up with something that relies a lot more on common notions and uses postulate 2 and stuff. Who knows? Somehow I doubt it's that he wants to come up with a way of making it longer than is necessary. Because we kind of know from Euclid, from Plato's line of school, that Plato likes simple and elegant proofs as opposed to long and tedious ones. Which, yes, I know, does beg the question, then why does he have to write out common notion 1 in full every time he uses it? But I don't have a good answer for that one. All right, let's take a look at proposition number 3. Because I said that proposition 3 is heavily related to this entire discussion we're having here. So proposition 3 is going to say that given two unequal straight lines, it is allowed to cut off from the greater a straight line equal to the less. So in other words, what Euclid is saying is something along these lines. Suppose we have a line here from C to D and a longer line from A out to a point B. What Euclid is saying in proposition 3 that it's allowable to do is AD is longer than CD. Therefore, according to this proposition, you can find some point, and here-ish, on the line AD, such that the length of the segment from C to D is going to be equal to the length of the segment from A to B. But given along that two lines, one of which is longer than the first, you can sort of cut off the longer line at a point for which this line right here is going to be equal to this one. And I think that's heavily related to what you were saying earlier, in that we're basically saying, hey, we can set this distance here, move it over somehow, and find a point on this line that's the same distance away from A as this one is. And I think once you have this proposition and it's proven, then I think Euclid's a lot more comfortable with the idea of setting your compass elsewhere, moving it over, and then being able to say, now draw a circle centered at A of this line. Because if you're able to find a point E like this that does that, once you get to here, now you can just say, oh, well then by postulate 3, now we can draw a circle centered at A that has radius equal to A. And so that would kind of answer the question of, from the postulates, do you know you can do this? Yes, but Euclid wants to explicitly prove it, and it's going to take quite a bit of work to actually get there. Any questions about this proposition? All right, we will prove this on Wednesday. So standard 4 quiz is not going to be due Wednesday, it's going to be due Friday. Had some really good discussion today. The proof for this one is not as long as the proof for 1 and 2. Probably do it in like about 10 minutes or so, but we had some good discussion today about these other questions. And so we'll hold off on the standard 14 quiz until after we finish, we go through proof of proposition 3, and then I have a few more comments to make. So in class on Wednesday, we will finish off standard 14 and probably start standard 15 in the second half of class. Where standard 15 is going to be looking at propositions related to congruent triangles, like side angle side and side and such. Hope you all have a good day. I will see you all on Wednesday.